Okay, today is day 2 on lesson 8.1, where we're doing logs and exponentials kind of at the same time. I am now in the part here where we have some examples. We're using the same file as yesterday for anybody following along at home. It's the same exact notability document. It's just like halfway through it, it starts day 2. And here are some examples of exponentials actually. 2 to the x, this one's e to the x. That seems really weird, but if you know that e is basically about 3, do you get 2 to the x and 3 to the x? They're pretty much, they're the same kind of problem, just a little bit bigger base. What is e exactly? 2.718. Okay, so 2.718, do you get how I'm rounding 2.7 to about 3? If we're sketching, isn't 2.7 and 3 close enough? Yes, for a sketch, sure. Okay. If you're going to use your calculator, then you may as well just type this thing into your calculator and graph it that way. Okay, so we're not doing that. I want to use 3 as my rough approximation for E. All right, so back to number 1, I had the kids start this because I told them, I know some of you have forgotten whether this looks like this, or whether it looks like this, or whether it looks like that, or whether it looks like that. And if you have the XY chart method, it's so handy because you can even forget what they look like and it'll tell you. So I'm going to put in something simple like 1. 2 to the 1 would be 2 plus 1 is 3. Did you have 1 comma 3 on your graph? Okay. I go over 1 and up 3. And that can be a little bit subjective on how far the marks are apart and stuff, but something like that. Then I'm going to put in a 0. Don't forget 0. It's really powerful because anything with 0 power is 1. 1 plus 1 is 2. Put in a 0, I get 2. Over 0, up 2. Now that's a straight line. I still can't tell whether that curve's up or down or where it's going to go from there. 3 points will help see a curve. Now let's put in 2. 2 squared is 4 plus 1 is 5. 2 comma 5. Over 2, up 5. That's starting to give me a feeling of a curve. You see what I'm seeing? I'm seeing a little bit of curve kind of like this. And that is what exponential graphs are supposed to look like. Now let's think about it. It was the exponential parent function, except what's that plus 1 doing? Shifting it where? Up 1. So the exponential graph had an asymptote there at 0, but don't you think when you moved it all up 1 that the asymptote would probably go with it? Yes. So the asymptote is now up 1, and the asymptote would be there. So what we need on these is an asymptote in the right spot, and then I'm going to say 3 points minimum. But honestly, if you can get 4, it's so much better than 3. Okay, so I'm going to just do one more point on this puppy. And don't forget -1. Why is -1 a good power to put in? Because when you put in a -1, it turns the other number into 1 over it. So what is 2 to the -1? 1/2. And 1/2 plus 1 is 1.5, and that's not hard to do. So -1 goes with 1.5. So there I am, and yes, now with these 4 points, I can definitely see that curve is rising as I go from left to right. Okay, so there's basically graphing. Here's another one, XY chart. You just stick numbers in. How is it getting any harder than that? Well, because we changed to logs later and throw negatives all over the place. What if we have a negative? What does that do to your graph? Flips it. Which way? Well, it depends. I want to remind you of something. This is inside with the x. Horizontal on inside. If the negative was on the outside, it would be vertical on the outside. High-vo. Kind of like the dwarfs. High-vo, high-vo. Off to transformations we go. Okay, that was terrible. But anyway, horizontal on the inside, vertical on the outside. So that's a horizontal flip of something that looked like that. Do you get that that would look something like that? Okay, and how about this one, which starts like this? You got to know that exponentials all look like this to start with. It's kind of like exponential growth, and they have an asymptote right there, except this guy's going to do 2 flips. I want you, some people are terrible at this. I want you to try to flip it both ways and show me what you think it looks like. On number 4, would you please give me just a rough, I just totally did a rough sketch of what the parent looks like. My question is, it does not look like this when it's done. It flips both ways. Tell me what you think it looks like. I want you to, in a moment, after everybody's got an answer, I want you to compare with the kid next to you. Wait till they've got it. Okay, here's what it should have looked like. First, you flip it. Well, actually, you can flip it any order you want, but I'm going to flip it that way first. And then I'm going to flip it left, right. I'll do it in green. Final answer. It'll look something like that in green. Do you get how I first went from the blue to the red? And then from the red to the green? If you do it in the other order, it still ends up in the same spot. Don't say, well, I did it backwards, so it's somewhere else. If you do it in the other order, it'll still be there. Yes, sir. You are correct. This one was not, this was me just talking about flips. I wasn't actually doing this problem. Okay, to actually do this problem, I will do the first with that problem. This horizontal on the inside is a horizontal flip, not a vertical flip. So this one would have a horizontal flip. It would look like that. I agree with you 100%. Okay, so that's a rough sketch. But when you actually find points, you'll dial it in much better. And how will you get your points? Next white chart. Okay, good. Well, what else do we need to know? Well, there's a bunch of, this one's more general. Instead of, a lot of times we do this in pre-calc. Instead of just numbers, you actually have to have these variables in there instead. Well, first, what does a log look like? I tried to tell you it looked like a tree that had been blown over in the wind. Looks kind of like this. You know what I'm talking about? Except you don't see many red trees nowadays, and maybe in the fall here in Minnesota, but okay. And that's a log graph. Now, what part of it would make it, would tell me its domain? Well, that's how far left and right it goes. Do you get there's an asymptote in there that's kind of blocking it? If you don't know this, there is an asymptote right here. So do you get it can't go forever to the left? So what's its normal domain? From 0 to infinity. How could this have gotten moved to the right? Would changing my base have moved it to the right or left? Nope, it just changes how steep this curve is. Okay, would changing the y, would changing that make it move up or down? It would move it up or down, yes. Because y is all about up and down. So if I subtract 1 here, do you get that's like, move it over to the other side, adding 1 to my log, and it would move the whole thing up 1? Okay, so y does mess with up and down. But what we were asking about here is domain, and it was 0 to infinity. So I just want you to be able to think about, okay, so what's going to move this right or left? Because that'll affect my domain. Only stuff that would be inside with the x would make this thing move. Do you get if my x changes, therefore, to x plus 1, that's going to affect my domain? All right. That would move it to the left or to the right and therefore affect the domain. All right, good enough on that. Next thing, if you're sketching logs, you need to know that they start like this. And this is a little harder to do the XY chart. It's still very important to be able to do it. And let me remind you of a few things. Some properties that you need to know about logs before I even try to do this. Because last hour I asked what log base 4 of 4 was, and they were like, huh? So I need to remind you of that before we try to graph these. So what is log base 4 of 4? 1, because it has a power right there of 1. Okay, what is log base 4 of, what's the next easy thing I could do? 16 would work, because then that's like 4 squared, and then that's the answer to that. 2. Do you get if this is y equals all that, that's really the same as y equals 2? They are identical. This is the same as this, because once you make that 16 into 4 squared, the answer to it is there. The answer is 2. This equals 2. Okay, so what's another good thing? Log base 4 of 4 was easy. Log base 4 of 16 was easy. What are some other ones that would work nice? Yes, ma'am. Log base 4 of 1. Excellent. Because when you've won the argument, I put a 1 in the argument, what do you always get? Nothing. You get nothing for winning your argument. Okay, so that one will equal 0. So that's a good one. One more. A lot of people never think of this one. Yes, sir. Yes, that's the one. Why is that particularly good? Because that's like 4 to the -1, and therefore what's this whole thing really equal to then? That is a -1 right there. So if it's y equals that, then that is -1. Okay, so now that we've kind of reminded you about that, let's go back here and let's make an XY chart for this funky kind of taupe and blue page. Problem 6. All right. You get that if I put a 1 in here, it'll work out really nice. So let's make the XY chart, and the X is 1. Why was that especially nice? Because log base 4 of 4 is 1. So 1 comma 1 would be on my graph. Put a dot right where about 1 comma 1 would be. Okay, Mr. A, tell me what to do next. Instead of putting in 1, I like it. When you put in -2, you got to strategically choose these. He chose that because that makes the argument 1. And when you've won the argument, you get 0, nothing. Okay, so -2 comma 0. I got 2 points. Can I tell which way it's curving yet? No. But I generally know what logs look like. Logs generally look like a tree blown over in the wind, which is kind of like this. So do you get this? Looks like a log that's been moved to the left. Oh, look at that. It is a log that's been moved to the left. So it looks to me like it's going to do something like that. But 2 points not enough. You need at least 3. So give me one more. We made the argument 1. We made the argument 4. Yes. 13. I like it. See where she's going with that? Because now it's log base 4 of total of 16, and that's really what? 2. 13 comma 2. Now I know that's way over here, but you get the idea. It doesn't rise very much. So if I go over what I think might be 13, something like that. Now I've got, maybe it would have been smarter to go to like -3 or something like that. Let's talk that through for a second. What if I'd have done -3? Can you have a 0 there? No, and therefore what happens? It makes an asymptote at -3. And does that make sense? Yeah, a log got shifted 3 to the left. They used to have an asymptote at 0. Now it moved to the left 3. So it actually kind of works out pretty cool, pretty logically. Okay, so there is my sketch of that. And notice, I didn't even have to be good at what the graph looked like. I did have to know some stuff like log base 4 of 4, and I have to understand those, but I didn't even have to know what the picture looked like. That's the power of an XY chart. Okay. This one, I honestly don't know exactly what that's going to look like, but I know kind of. Would you agree it's kind of like that, except moved where? Up a couple. Okay, so it's kind of going to look like that. How am I going to know for sure what it looks like? XY chart. Okay, good enough. Moving on to, these are more of the same. It's just ln. I told you yesterday to replace that with log base E. And for the purposes of sketching, E is about what? About 3. 2.718, but it's about 3. So this is like log base E of x minus 3, which is like log base 3 of x minus 3. It's okay. It's close enough. You don't have to be perfect on those. If you had a calculator to do it with, then you just type the whole thing in the calculator. You know what I mean? Like you wouldn't be sketching it. If we gave you a calculator, you'd be just graphing it on the calculator. Okay, good enough. Now this property stuff is the last thing I have to talk over before we start the homework for tonight. And this is super important. These are hard to, like, there's so many things to know about logs. And I'm going to go through them with examples. I'm going to put an example underneath each one of these, and that's what I would recommend you do. A typical problem you'd have to do using this little rule. So here's a typical problem you'd have with this. You'd have log base 2 of, let's say, x times p. Well, this property of logs says that you can break things that are multiplied here, where you have an argument that's two things multiplied. You can break them into adds. Would you please write this? If you're doing this just on paper, write an example for each of these and try to answer it. Would you please try to answer what that is by looking at the property? Try to answer what you think that is on paper or virtual paper right now. All right, log base 2 of x plus log base 2 of y. So basically we, oh, p, sorry, p, you said p. That makes sense? Basically, if you have things that are added, sorry, if you have things that are multiplied, you can change them into add. So if you have things that are divide, what do you think you're going to do? Subtract and subtract. So this should be easy as pie. Log base 3, that base doesn't matter, you just have a base, of x over 9, let's say. Would you please break that up into 2 logs? This is called expanding because we had 1 log and now we're going to have 2 logs. Log. Okay, and since it was divide, it now changes to minus, and the base 3 stays the same, and then it's x and 9. There we go. Now, just a little side note, this one is not expanded all the way because that 9 could be thought of as what? 3 times 3. You get how then you could break this up into 2 more logs. This log could be log base 3 of 3, which happens to equal 1, plus log base 3 of 3, which happens to equal 1, which means 1 plus 1 is really 2. So couldn't I just gone to 2 right in the first place? Yeah, it would have been smarter instead of saying 3 times 3 to say 3 squared, and then you go, oh wait, those are the same, so it equals 2. But all those properties, I hope they're starting to come together to see how that we can prove that that equals 2. Okay, moving on. You don't have to be a master of this yet, but we're starting to, this is day 2 where you dig in deeper. So this is where I have log base 3 of, let's say, 5 squared. That's a typical question. Do you get how I could change that 5 squared into 5 times 5? And then I can have 2 of them, and then I could say I have 2 of the exact same thing. What this property says is you could skip all that rigmarole. Just move the 2 down in front. 2 times log base 5 of 3. I'm going to show you why in a second, but just do you get that the power went from here to down in front? I'm going to show you why now. Do you get 5 squared could be thought of as 5 times 5? And do you get that that could be broken into 2 of them? Log base 3 of 5 plus log base 3 of 5. And if there's 2 of the exact same thing, couldn't you say 2 log base 3 of 5? Yeah, that's why you could have skipped all of that and just gone right from, if that's a squared, drop squared down in front and say 2 of them. Because otherwise you're going to have to go all through all that work and then combine them together and say 2 log base 3 of 5. So the powers can drop down. That's called the power rule. Number 4. This one is that change of base. I showed you yesterday, and most of you took to it right away. You remembered it from last year. If I have log base 3 of 7, do you get that that's really log 7 over log 3? What did they do in this example that I never did? They wrote base 10. Do you get if I just say log 7, it means log base 10? Okay. So this is just the one that says that you can write this as log 7 over log 3. And if you want to, you can say base 10s on them. Here's the inside secret. You can actually say base anything you want. Don't have to be base 10. They could be base E. They could be base anything. And your calculator actually knows two bases. It knows base 10 and it knows base e, which is about base 3. Okay, so if you wanted to, you could do ln 7 over ln 3 and it would also work. Didn't know that, did you? Good question. Let me give you this example. This comes out to some number, right? Some answer of like 4.6, some number. If the number on the top is bigger and the number on the bottom is bigger, it could still come out to 4.6. When you have bases that get, well, e compared to 10, do you get one of them is bigger than the other? Base e is about 3 and base 10 is about 10. The bigger the base is, the smaller the number is. And so when you use different bases like this, it's just the numbers are both bigger, but when you divide them, it all works out. It's kind of like, let's say I wanted to get the answer of 2. Do you get that could be 4 over 2, or it could be 8 over 4. Both numbers are bigger, but they still ratio comes out to 2. So in the logs, if one of the logs has a bigger, if I decided to make the bases be bigger, that actually gives me smaller decimals. If both decimals are equally smaller or proportionally smaller, it's okay. So bottom line, you don't really need to use this a lot, but that can be base anything you want. We just usually use base 10 because it happens to be the most common log. But it could be base e. So a really complicated, like, sounding question would be, take this and write it in base 23. Be like, oh my gosh, that seems impossible. And it's just log 7 over log 3. And I just told you, you could make the base any size you want because it's going to proportionally make each number bigger or smaller. And so therefore, you can make it base 23. And that's, there you go. I just made it into base 23. But it's still equal to the same thing as if I had said base 10. Now, my numbers, when I make the base smaller, my answers actually get a little bigger. Kind of counterintuitive there. And both answers just got a little bit bigger. And so when I divide them, they stay the same. Okay. So back to my little properties I was talking you through. And I wish that I didn't have to teach you all of this at once. But by tomorrow, that means that you'll be able to pull a lot of things together. This one's really simple. If these are the same, then the answer is the power that's on it. I'm going to pause for a second because I got a visitor. All right. So if this had been a 4 up here, then the answer would have been 4. Remember, if the bases are the same, the answer is whatever exponent's on it. But, Mr. Server, that didn't have an exponent. Yeah, that means it has a 1. That means the answer is 1. Okay? So that property is just saying if the bases are the same, the answer is whatever the exponent is. This property is the one where you won the argument, and so you get nothing. Remember that one? Put a 1 in the argument, you'll always get 0. This property is, these are going a lot faster now, which is wonderful. This property is that if you have a 0 here, there's no answer. It actually, there's a whole bunch of things you could do to screw these up. Remember how you can't have zeros or negatives, or what's one more thing that can't be loud? The base can't be 1. Good. That cannot be 1. Can't be 1, it can't be 0, it can't be negatives. These guys, they can't be 0 or negatives. That's our 12-minute warning. All right, and this last property, before I can jump in the homework with you, is that if these bases are the same, that also works. The answer's already there. It's a complicated explanation, but I'll give you an example problem. 8 log base 8 of 9, the answer's 9. Do you see how that's a base, kind of? And this is a base of the log. And that's my way of remembering that, is if the bases are the same, the answer will already be there. The answer is the other thing. In this case, it's that. In that other problem, it was like log base 3 of 3 to the 5th. Those are both bases in their own right. One's the base of the log. The other one's a base having a power on it. And if the bases are the same, the answer's already there. Different kind, but. All right. That's all the properties that we are expecting you to know so far, anyway, of logs. And that's a lot. I get it, because you just have had this is your second day of logs. And it would be like day 9 or 8 last year. So condenses a lot down into quick. All right, so here's your homework. and there's a few too many. 58 and 60 are both good, and it looks like you have to graph two things. Not really. That's just the parent function. They really just want you to graph that. They're just reminding you the parent function was 2 to the x, and then graph that. Now, it actually tells you a different way of doing it. It says graph this one and then move all the points. That does work. Do you get if I graph that one and then move all the points down 1? It would work. But I think it's more powerful to just skip the middleman, just graph that one by making an XY chart. I think that's the best way to go. All right? So you really don't have to graph this. It's just reminding you that's the parent function. Same with this one. You don't have to graph that. It's just kind of like the parent function. Just make an XY chart. And you should generally know that that's a power function. When you throw a negative in there, I do want to explain that real quick. You can just use, stick numbers in, see what happens. If I stick in a 0, it's 3 to the negative 0, which is like 3 to the 0, which is 1, plus 2 is 3, 0, 3 is on your graph. You can do that, but if you think this through, that's not exponential growth anymore. What do you think it is? When you have a negative up there, it turns it into exponential decay. So here's growth. That's exponential growth. Here's exponential decay. Do you get how the negative makes it flip left-right? Do you get how it's going down as we read from left to right? Decay is things going down as you go from left to right? I think it makes sense if you think it through. The blue one here is the reverse. It's going from exponential growth, changes it into exponential decay. All right, so there's a few more that I want you to do. I do want you to do 62. It's kind of backwards, and so I think if you use the XY chart method, this won't baffle you at all. You'll be able to do it just fine. But kids that try to move it, do you get how they tend to move it down 8, even though that's not right? The 8 is actually a positive 8. The negative is on the E, so that's actually a reflection. But all that gets worked out if you just use an XY chart properly. Okay, moving on to this and this. I think there's a few too many here. You could skip 66 and 68. Then on the next page, you may skip this entire page. I may talk to you about that at some point, but I'm not today. Now, the Richter scale problem. I did do that demo at the beginning of the hour, so I'd like to leave that problem in there. It's a real good one. And I will let you skip D as in dogfish. It really bothers people. There is such a thing as a dogfish. Just like there's a catfish, there's a dogfish. Anyway, so you can skip D, as in maybe I should have gone with dolphin. And you may skip 76 and 77. So I'm chopping off a few word problems, but I really want you to do a quality job on number 75 since we've talked about it today. Now, you might get confused. There's really only two places you can put stuff. You can stick stuff in there, or you can stick stuff in there. Okay? And you're welcome to use a calculator when you do this. It's fine, because you're going to get weird decimals and stuff out. But it tells you what X is. It says right here, X is the seismograph reading in millimeters. And M of X must be something else, which it'll tell you. You just have to read it thoroughly. Okay? All right, that's all I got for you for today.